All right, let's talk about the Ethernet specification. Maybe some of you have heard about this, or you've heard the term Ethernet. This is something that's quite common, and will come up a lot. So again, should be something that you're familiar with. All right, so 3 topics we're going to cover. Okay, yeah, you understand the term. So you heard the term, but you don't know the meaning. So tonight is a special night because tonight you're going to learn the meaning of Ethernet, and you're gonna know it better than you ever knew it or hope that you'd ever know. So let's hope. We will try for that. All right, so we're going to talk about the Ethernet basics. We're going to define what Ethernet is at a high level. And then we're going to look at the reason I wanted to go back and cover the OSI model, because the Ethernet specification exists at 2 levels. It exists at the physical level, and it exists at the physical layer and at the data link layer. So I wanted to go back and make sure you understood that, because we're going to come back and talk about now how a specific standard, how a specific communication standard applies to a more generic model. So the OSI model is a logical, generic model, but the Ethernet communication standard is an implementation of that standard, but just at 2 layers, at the physical layer and at the data link layer. Okay, but you'll see when we talk about it why it's so important for us to talk about. All right, so Ethernet is a communication standard for network devices that are wired to a local area network. All right, and I say wired because I want to be clear that this is a distinction between Wi-Fi type of protocols or standards or standards. So it's some of you in your homes or in your offices may be wired to a network, and we're going to look at some of the cables and devices that are associated with Ethernet, but some of you may be wired. If you're wired to a network, then chances are you're using the Ethernet communication standard. If you're not, then you're using something else. And just as an aside, there is another protocol, we'll get to it in a second, which is for the Wi-Fi standard. But Ethernet is a communication standard for a wired host within or wired communication within a local area network. And as I mentioned, it is it's specified at the physical layer and the data link layer. Okay. Now, it was formalized in the mid-'80s, around 1985, by the Institute of Electrical and Electronics Engineers, known as IEEE. And the standard, this is a number you should remember, the standard is called IEEE 802.3. So when anybody refers to 802.3 or Ethernet, they're synonymous. They mean the same thing. And as I mentioned, there is another standard for Wi-Fi, and that's known as 802.11. Okay, and I just want to make that distinction because this is a wired network versus wireless. Now, when it first started, it was started with coaxial cable, but then eventually evolved to include twisted pair, and I'm going to show you examples of those. Okay, so we're going to cover both cables and devices at layer 1, and then at layer 2, we're going to talk about some of the devices and protocols. All right, so Ethernet is a very detailed specification. So the idea here is to make it so that you understand it a lot better than you did when you walked into this class, but we can't go into all of the details of Ethernet. So we're going to cover as much as we can to get you a deeper understanding of it. But it's a very very broad and very detailed specification, but we're just trying to get you a good understanding, a solid understanding of what it does. And so we're going to cover some of the things that it does and it defines. And once again, it's defined at 2 different layers, at the physical layer and at the data link layer. So at the physical layer, it's going to define the cabling that you can use and the connectors you can use. Okay, it goes down to that level, the cables and the connectors. And then at the data link layer or or layer 2, it's going to talk about how to do MAC addressing. So we just finished talking about that. And so this protocol is going to specify how to do that MAC addressing. Okay. It's also then going to talk about how to actually interface with the physical layer and put data onto the physical layer. Okay. And then how to create those data frames that we talked about. Okay, so we're going to look at all those different aspects of the Ethernet specification. All right, so let's start at the physical layer, and this will probably be the kind of easiest to understand. So at the physical layer, it defines cabling and connectors. So for example, you see, first of all, and sorry, I've got multiple screens going, so I have to sometimes turn my head. But you'll have a certain amount, a specified bandwidth, okay? And then associated with that bandwidth is the name of the, or common name of that protocol, and then an informal name, and then the specification or the IEEE name. So let's start at the top here. This is the slowest bandwidth or the lowest bandwidth. And so if we start with 10 megabits per second, okay, this is known as the Ethernet standard. The informal name is 10 base T. And we're going to get into what some of these, digits and letters in this name mean. But 10, for example, tells you that it's 10 megabits. So for example, we go to 100 here, 100 megabits, 1,000 megabits. We've got 1,000, 1,000, 100, and 10. So that tells you the speed, okay? Yes, bandwidth is how much data you can transfer per second, correct? Okay, it's they talk about bandwidth or the pipe size. Sometimes somebody will call it the size of your pipe. How big is your pipe? But that's how much data you can transfer per second. Remember, we talked last week. There's two measurements of network performance. One is bandwidth. That's how much data you can push through in a period of time or every second. And then there's latency, which is the amount of time you have to wait. So if you have latency, let's say I have one node in let's say New York and one node in Los Angeles, the fact that you've got a physical distance between those two nodes means there's going to be some latency. It might be very small, but there's going to be some latency. So even though I'm pushing through 10 megabits per second, it might take 2 seconds for my request to get across. So after that 2 seconds, it's going to come through at 10 megabits per second, but there's a latency of two seconds. So there's a difference between bandwidth and latency. One is a delay, one is throughput. But yes, you're correct, Ice. Bandwidth is how much data is transferred per second. And the type of cable that we used is called an unshielded twisted pair, or UTP. And most often, or more often than not, you'll see them referred to in these CAT, or these categories. And so this is a Cat3 cable that gives you a maximum distance of 100 meters. So if you need to go beyond that, you need to put something between those two nodes, like a repeater or a hub or something else like that. And then you have a connector, which is an RJ45, which I'm going to show you in just 1 second. Then you're going to go to 100 megabits per second. It's called fast Ethernet. 100 megabits per second, it's gigabit Ethernet, because 1,000 megabits is 1 gigabit, but it's called 1,000 Mbps. But you can see in this case, this is 1,000 based LX. This is a fiber specification. So the cable in this case is fiber, whereas in this case, it's going to be copper, category 5 or category 3 copper cable. Okay. And then you also have 1,000 Mbps, but this one is 1,000 base T because it is using copper. Okay, and the connectors here are slightly different, either SFP or SC. And again, I'll show you those in a second. And then you go to 10 gigabits per second. Okay, here you've got 10 gigabit Ethernet. Now you see it changes from 1000 base or 10 base, it goes to 10 G base. And again, you can use the same Cat6 cable with 100 meters of or 100 meter range. Okay. So the number in front of this name here gives you the speed. And in a minute, we'll talk about what this term base means. Okay. Now, I want to show you what these cables and connectors actually look like. So now you should say, okay, I see what you're talking about now. So this is the raw, unshielded, twisted pair. If you were to open it up, this is what it looks like. But this cable, most, if not all of you, should have seen, right? So if you're on a wired network, you should have a cable like this that plugs into your computer and a port that it plugs into. And that port is your network interface card. Fiber optic, which you're not going to have in your office, but if some of you have audio systems, you'll have a fiber optic cable for that. But fiber optic normally comes in from your ISP, and this is what the cable would look like. This has multiple channels, and these are what the connectors would look like. This is an SC connector here, and this is a SFP connector. Okay. But that's the physical layer of the Ethernet specification. And then the other thing to understand here is the difference between broadband and baseband. Okay, so in baseband, essentially you can think of baseband as digital signals and broadband as analog signals. Okay, digital signals are ones and zeros. Analog signals are continuous waves. They're not just 1 or 0. It can be a number from 0 to, we can go up to any arbitrary number, but it's an analog signal. So if you understand the difference between analog, digital, great, it should be obvious. But if not, just think about digital as either a 1 or a 0, and analog can be any number. Okay, think of a sine wave if you've seen a sine wave before. Okay. But in baseband, okay, baseband is digital. So baseband data is sent as digital signals through the media as a single channel that uses the entire bandwidth of the media. Baseband communication is bidirectional, goes in both directions. Okay, so the same channel can be used to send and receive signals. So the entire bandwidth of that cable is used to send signals. That means everybody's sharing the bandwidth on that single cable back and forth. Okay. So broadband, on the other hand, is going to send information in the form of analog signals, and each transmission is assigned a portion of the bandwidth. So you can put multiple signals on a particular cable, but you only use a portion of the bandwidth. But broadband is an analog signal, and you're sharing the bandwidth amongst multiple signals, right? So you can see here in digital, it's just one signal, and here you can see multiple signals. Here it's digital, it's 1 or 0, whereas here it's a continuous wave. Okay. So broadband communication is unidirectional. In order to send and receive, 2 pathways are needed. You need one for send and one for receive, or you can assign different frequencies. Because these are waves, they have different frequencies. So you can have either put 2 different cables or use the same cable and use different frequencies. Okay. Baseband is used for short distance of data transfer, and the entire bandwidth is used, as I mentioned. All right. Broadband is going to be used for long distances for data transfer, and the entire bandwidth of the cable is used for multiple signal transmission at different frequencies. All right. So if you're using a broadband internet connection from your home internet, what happens is that broadband is brought to your router in your house, or you have a broadband to connection, and that broadband connection is terminated there. And then inside your house, it's going to be what? Baseband. Baseband is used for short distances. Okay, and that's what's going to be inside your house. So if we go back up for a second, and then we can take our break. If we go back up here, you see this here, base, 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 base. That tells you this is for baseband. So that tells you that Ethernet specification is for, these cables are for baseband communications. This is all digital communication. So the 10 tells you the speed, megabits. 10G tells you it's 10 gigabits. And then the base tells you it's baseband instead of broadband. Okay, so that's all the layer 1 stuff that is associated with, well, not all the layer 1 stuff, but the layer 1 stuff we want to talk about that's related to Ethernet. So the cabling standards, you know, how some of the names of those standards come about, the different speeds or bandwidth, if you will, and then, you know, transmission via baseband. Okay. So now we have this layer 1 meet layer 2. So this may or may not look familiar to you, but here's the RJ45 connector that we were talking about, right? Here. So this is some kind of a hub. This is a laptop, and this is a desktop. How many of you have never seen something like this before? I know I'm old, but I'm hoping that you guys have seen this before, because it still exists. I have. Okay, good. So I'm not talking very theoretical. Okay, good, great, perfect. Okay, so this is now what I broke when I was in high school. Okay, all right. So this is your cable connecting to your NIC card. Okay, so you remember when we talked about layer 1 and layer 2 in the summary on the OSI models, right? Layer 1 was the physical. The physical is the connector and the cable. And layer 2 was what? Layer 2 was MAC address to MAC address, or network interface card to network interface card, NIC to NIC. So this is where layer 1 meets layer 2. What's on the other side of this connector here is a network interface card. Okay, so now we're going to go on to talk about layer 2. Layer 2 with regards to Ethernet. Okay, so there are 3 things that we're going to look at with regards to the data link layer. 1 is device addressing. Then we'll look at data access frames. Actually, second, we'll look at the media access control, which is very critical. And then we'll look at the end, data frames. I have these in a slightly different order here. Okay, so let's look at the MAC addressing. So Ethernet at the data link layer is responsible for Ethernet addressing. Commonly, it's known as hardware addressing or MAC addressing. So I've used this term many times now, and it's today, so you should be a little bit clear on what that is. Every single network interface card has a unique MAC address. And so the Ethernet is then responsible for defining that address or putting that address into the frame, as we talked about, and sending it along. Okay. Now, what we're going to do next is, for those of you who like math, it's going to be great. For those of you who don't like math, just plug your nose and try and figure out how we're doing it, because it's important not only for MAC addressing, but when we start talking about IPs and internet or IP addressing, that's going to be important. But main thing to understand here is that the Ethernet protocol is responsible for coming up with these MAC addresses. Okay, so the MAC address, as I mentioned, actually I didn't write it here, but as I mentioned in the previous session, it's made up of hexadecimal numbers, right? So we're going to talk about, and remember, when we go from the data link layer to the binary or to the physical layer, we're going from data into ones and zeros, into bits. So we have to be able to convert from hexadecimal into binary in order to be able to do that. Not quickly, all the time. Ethernet needs to do it quickly. We don't have to do it quickly. You just need to understand on how to do that. Okay, so understanding the differences between binary, decimal, and hexadecimal, and how to convert from one format into the other is important before we discuss the TCP/IP protocol, and it's also important as part of Ethernet. So you should know that in binary communication or binary math, you're going to have a bit that's either 1 or it's going to be 0. Okay, and typically you're going to put 4 bits together, or you're going to put 8 bits together. If you put 4 bits together, it's often called a nibble. When you put 8 bits together, it's called a byte. Okay, so that's simple. When you have a binary number, you can only, just like if you have a decimal number, you can have in any one place, you can have a digit from 0 to 9, right? That's 10 numbers. That's the decimal system. In binary, you can have in any one digit, in any one place, you can only have a 0 or a 1. Okay, and then you put 4 of them together, you get a nibble. You put 8 of them together, you get a byte. Or yeah, byte. Sorry. All right. So here's some examples, and I would say, I would strongly suggest that you memorize this this table here, because this is going to be important when it comes to IPs. So, you'll get the slides, you can take a look at it, but essentially, there should have been one more table before this one, but let me see, how can I do this? Yeah, I think let me just pull up something to write on and share it with you. I didn't realize, I didn't look at this slide carefully enough. I thought it was starting from 1. Okay, so you should be able to all see my scratch pad here. I'm going to make it a big font so you can all see it. So if I have the digits 1, if I have 1, 2, 3, 4, 5, 6, 7, 8. That's 1 byte, right? So I can make this bit, I can make it either 1 or 0. Okay, so I'm going to make it 1. Okay, so what is the value? So if this is 1, just imagine these are all zeros. So if this is a 1, then what's the value of this entire byte here? It's just 1. Okay. If I do the same thing, except no, it's not 0, it's 1. If I put the 1 here, and I put a 0 here, okay, now it becomes 2. Okay. Now, if I put the 1 here, and I put the 0 here, that becomes 4. Correct. So when you're doing binary, every time you shift the 1, every time you shift it left, you're multiplying by 2. So this is 1, this is 2, this is 4, this is 8. So all you have to do is you have to look at wherever your 1 is, and you just do 2 to that power. So if 2 to the power 0, because that's in the 0 position, that would be 1. 2 to the power 1, because that's the first position, that's going to be 2. 2 to the 2 is going to be 4. 2 to 3 is going to be 8. Okay, so if I look at the position numbers, this is going to be, yeah, I'm sorry, I should have looked at that slide a little more carefully. This is going to be position 0. This is going to be position 1. It's going to be position 2, position 3, and so on. So if you want to know what the number is, essentially you do 2 to that power, right? So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Okay. So if I come back to this, here we have 2 to the 0, 2 to the 1, 2 to the 2, 3, 4, 5, 6, 7. Can somebody tell me what 2 to the power 7 is? Do it on your calculator. Yeah, 128. So this is 128. Okay. Now, how do we get to 192 here? So ignore everything. Okay, just look at, so we know this bit represents 128 here. What does this bit represent? So this is going to be 2 to the 6. What's 2 to the 6? 64, correct. So now we're going to add 128 plus 64. That's 192. Yeah, nice, you got it. Okay, looks like you guys understand it. Well, some of you. But if you don't understand it, at the very least, you should memorize this table. But better you understand how to do it. So that's right. This would be 2 to the 7. This would be 2 to the 7 plus 2 to the 6. This would be 2 to the 7 plus 2 to the 6 plus 2 to the 5, and so on and so on and so forth. Okay, and I could easily go the other way. I could go from 1 to 255 or 1 to 128. Okay, but that's the way you convert from binary to decimal. You just take 2 to the power of whatever place it is and add those values all together. Okay. If there are any of you who think that you want more practice with this, then just let me know and I can either give you some additional exercises or we can cover it a little bit more detail next week. But this is very important to be able to go between binary and decimal and then back to hex. Okay, so sounds like a lot of you understand how to convert to from binary to decimal. So now let's talk about binary to hexadecimal to decimal. So for, thank you, Rabia. So and Rabia has put a link in there if you want some help on going to binary. But let's look at binary to hex to decimal. So in order to get a hex value, you need 4 bits. Okay, 1, 2, 3, 4, 4 bits. So what's the binary value here? Well, I don't have any ones, it's just 0. So the decimal value is 0 and the hex value is 0. So it's going to go, so the decimal and the hex value is going to be the same. Okay. So if you look at, let's look at 7 here. Okay. So here I have 1 plus 2 is 3 plus 4 is 7. So that gives me 7. So a hexadecimal can go from 0 all the way through 9, and then it has to go to the alphabet. So now I get 8. So this is just going to be 8. The top bit here is going to give me 8 decimal, 8 hex. And then I add one more, and I'm going to go to 9. So this is 8 plus 1 is 9. Now, when I go to 10, there's no 10 in a hex. So now I'm going to go to A. So it goes 0 through 9, 0 through 9, and then A through F. Okay, so as soon as I get through to 9, they're the same. And then when I get to 10, the hex value for 10 is A, for 11 is B, for 12 is C, 13 is D, E, and F. Okay. I find it easier just to go, as soon as I go above 9, just to kind of memorize how, 10 is A, or count up. If 10 is A, then I know counting up to 15 how to get to F. Okay, F is easy to remember. Okay, so that's how you're going to go from a binary value to decimal to hexadecimal. You're going to take it in chunks of 4 or nibbles. That's why we talked about the nibble. Each nibble is going to represent one hex digit. So this nibble represents the hex 0. This nibble here represents the hex F. This one represents hex E. All right, let's do an example here. We're going to convert, we want to convert from 04E, okay, OX. So these are two different ways of, by the way, these are two different ways of writing hexadecimal. You can either write 0x, that signifies that's hexadecimal, or you can put an H, and I've also seen a capital H here behind it. So either small h or capital H, and that tells you it's hex. Okay, so you have to take these, remember these, each hex digit corresponds to how many binary digits? 4, a nibble. Each hex digit corresponds to a nibble. So this is going to be 2 hex digits here. So I'm going to have 1 nibble and 1 nibble, or 4 and 4. I'm going to have 8 bits or a byte at the end of this. I should know that. So what is 4? Well, if I convert 4 into decimal, that's easy. 1, 2, and 4. Okay. And if I want E, it's going to be, you can count up from 10, or you can say it's F minus 1. So I'm just going to take away the 1 from here. Okay. Or as mine says, it's 14. Right? A, B, C, D, E. 10, 11, 12, 13, 14. So that's 14. Right? So that's why it's important to be able to go from decimal to binary. So now I know what 14 is, so I can write that. So now I just put them together. 4E. So 4E hex is the same as that in binary. What is it in decimal? So we've got here, we've got 1, we've got 2, plus 4, plus 8, plus 64. What's that? 2, 4, 8, and 64 is 78. Okay, if 78, then that's the right answer. Okay, so 4E is that in decimal, and then it's 78 in decimal. Okay, all right, good. All right, so take a minute. I'm going to give you a minute, and then I'm going to work out the answer on the screen here. But don't write the answer in Slack. I'm going to look at my watch. I'm going to give you, well, let's say 45 seconds, or let's say a minute. I'll give you a minute. Start now. Don't type the answer. Just put it down, do it on a piece of paper, and then I'm going to work it out here together with everybody so everybody can see how it's done. Because if you start typing the answer, then other people are going to be distracted. So just put it on a sheet of paper. 27 hex. What is the value in binary? Okay, it's a little bit over 45 seconds. So let's work that out here. It's 27 hex, right? So this one should be relatively easy. If I've got 27 hex, okay? So I know I'm going to have 1, 2, 3, oops, 1, 2, 3, 4, and then I'm going to have another. I'm just going to put a bar just so we can split them up while we're doing this. 2, 3, 4. So I need to know what is 2. Well, 2 is easy. 2 is just a 1 here, right? And what is 7? Well, 7 is just going to be 1, 1, 1, and 1. So that's 7. And then the rest of them are going to be zeros. Right? So the correct answer is 0, 0, 1, 0, and then 0, 1, 1, 1 in decimal. Sorry, in binary. And then if we want to know what it is in decimal as an extra exercise, we're going to have, we already know this is 7. I can get rid of this bar here. 7 is going to be 8, 16, 32. It's going to be 7 plus 32, right? Plus 32 equals 39. Am I right? Okay, I's got something else. E got, or she, sorry if I got the 0, 0, 0, 1. No, so you need the 2. This is 2, so you need to get 2 first. Okay, this is the 2. Where did you get 1B from? We're not doing 1B, we're doing 27 hex. So this is 2, and this is 7. We're not working on 1B. No. 27 hex is the same as 0, 27. This is already hex. These two mean the same thing. Okay. And then that's going to be 39 decimal. Okay. All right. Hopefully that makes sense to everybody. Let's look at the next one. Okay, what is the binary value of hex F9? Okay, so I'll give you another minute. Say another minute. We're doing 0 F9. So you can look at it as either 0x F9 or F9 hex. Okay, it's the same thing. And we want to get it in decimal. Sorry, in binary. Okay, we're doing F9 or 0x F9, same thing. Okay, so we're going to do F. F is easy. F is all 1. So we're just going to make 1, 1, 1, and 1. And then if we want 9, we have 4 bits. To get 9, we need a 1 and we need an 8. So the last one is 8. So that's 9. So it should be that 1, 1, 1, 1, 1, 0, 0, 1. Yeah. Mine you're missing your, no, you don't have the F right. That's E. You have E, not F. Okay. And if we want to convert it to decimal, this is going to be 1 plus 2 is 3 plus 4 is 7 plus 8 is 15. And on the other one, we're just going to have 9. Oh, sorry. No, that's not right. Oh, boy, I messed this one up too. Ignore this. It's a little bit more complicated. This is going to be, yeah, someone would have to add all these digits up. But anyways, that's the F9. To get the decimal, we have to do 1, 2, 4, 1 plus 8 plus 16 plus 32 plus 164 plus 128. Sorry, the previous answer I had wrong. I don't know what I was thinking. Okay, but anyways, we just need to get the binary, and hopefully that gives you a sense of how to get that binary yeah, binary from hex. All right, good. Okay. So let's go through this in a little more detail again. So again, Ethernet addresses, okay, are called MAC addresses. And by the way, MAC stands for Media Access Control. Media Access Control. And you'll see why shortly. MAC addresses. Each network device has a unique MAC address. All right, so don't forget that. IP addresses will change, but MAC addresses are globally unique. So you remember when we're sending at layer 2, we're sending a frame. So we're going to send an Ethernet frame. We add our own unique MAC address as the source, and then we add the MAC address of the receiver as the destination. Okay. MAC addresses are unique 48 bits, are unique 48 bit for a particular network device or a network interface card during the time of manufacturing. Okay. Sometimes people call this a physical address of a network device or a MAC address. Those two are interchangeable. So you're going to see the first 3 hex or the first half, the first 24 bits, the first 3 bytes are going to be for the manufacturer. And then the manufacturer can make, put whatever digits they want here, but when you put them together, they're going to be unique. You remember I said you have the Ethernet frame has to contain a source and a destination MAC address, right? So there are 3 different ways that you can send a message. You can, first of all, at the data link layer. So first of all, you can do a unicast message, which means I'm going to specify the NIC, specify a specific NIC on the network, and I'm going to have 1 sender, which is myself, and only 1 receiver. So that's unicast. Okay, so I'm just sending it to 1 particular machine at a time. Okay, these are different messages. So first thing I can do is unicast. The second thing I can do is multicast. So in some cases, I might need to send messages to multiple devices. So in this case, you can see I'm sending the message to multiple devices. Okay? So in this case, it's 1 sender and multiple receivers. And then the last option is to do a broadcast. So a broadcast is very common. So let's say, for example, I put a new computer onto my network. and I need to know what is, and some computer needs to send me a message. How does that computer know, let's say they want to find out what my address is. How do they find out what my address is? Or if I have because they don't know me yet, I've just plugged myself into the network. So the way information like that is gathered or disseminated is by broadcasting. So essentially, you might broadcast, this is my MAC address, or sometimes when we get into IP addresses, we'll talk about how we do MAC to IP address conversions. Somebody will say, here's the MAC address. Can you tell me what your IP address is? And so you'll have to do a broadcast. And so if you want to do a broadcast, your MAC address is changed to this, and that gets sent to all of the different network devices on the network. Okay, so you can do unicast, multicast, or broadcast. I'll have to think of a good example for what a multicast might be, but those are examples of unicast is obvious, and then broadcast is if you don't know, you don't know a device exists, or you want to know something about a device, but you don't know information about it. You just send it to everybody, and then whichever device needs to will respond. Okay, so that was the math portion of this session. Hopefully it made sense. And some of you, it looks like might have to go back and do a little bit of a refresher of binary to hex and hex to decimal and decimal to binary. It's not that difficult, and you don't have to, memorize all of it all the time. You just have to know some basic rules. So just go back and do some refreshers. It'll help you out. And if you want some exercises, someone posted that website, you can check that out. But if you get stuck, then just reach out for help. All right, let's look at the next thing, which is media access control. So this is very interesting. This is how we're actually putting data, how we're interfacing with the physical layer. Okay, so the protocol that's used to transmit frames is called CSMA/CD. So that stands for Carrier Sense Multiple Access Collision Detection. That's the protocol. Now, it sounds like a mouthful, but it actually makes a lot of sense, because this protocol is based on the fact that multiple devices can simultaneously access the same media, but only one can transmit, right? So if I have one piece of wire, remember what we talked about, baseband, you can only send one signal at a time. It's not broadband, it's baseband, so you can only send one signal at a time. So only one of these machines can send information at one time. So, but they can all access it, and only one can send it. So that means this protocol, or these machines, should be able to sense when there's an existing transmission on the line, right? That's where this carrier sense comes from. So it's carrier sense with multiple access. And now, on the chance that two machines send data at exactly the same time, that's going to mess things up. So that's where the collision detection comes in. So we've got multiple access, but carrier sense with collision detection. So you've got to be able to detect a collision in the event that something else puts a message on the wire at the same time. CSMA/CD, carrier sense multiple access collision detection. That's the protocol. And let's look at some examples. It's pretty straightforward how it works. All right, so we have a sending device here. Let's say it's this device here. Okay, it's going to first do what? It's going to sense. Is there anything on the wire? Okay, if there is, then it's just going to wait. So it's not going to do anything. No big issue there. In this case, we're doing an example without collision. So let's pretend there's no collision. So if there's nothing on the wire, So if it's not busy, then send the frame. Now, remember what I said, there might be a situation where two devices put a message on at the same time. So you have to detect if there's a collision. In this case, we're saying there's no collision. So it's not busy, so it sends the frame, and it's going to monitor the wire for other signals. Okay. In this case, there's not going to be anything found because there's no collision. And all of the other devices are going to receive the frame. Each of the devices is going to check whether the MAC address matches its own MAC address. And if it does, it's going to continue processing. And if not, it's going to discard the frame. So let's say 2 was putting on a signal. Okay. It detects if it's busy, it's not busy. It puts something on, doesn't detect a collision. And so all of these different machines receive the packet. It was destined for machine 4. The MAC addresses match. And so then it sends that frame up the chain for processing. Make sense? Okay. Sense, transmit, detect collision. Okay. All right, now let's look at an example when we actually have a collision. So again, this time 2, yeah, we're going to talk about what the frame includes in the next section. But what's the one thing that the frame exists that you should know? What is in that frame that you should know besides everything else? There's one very important piece of data that has to be in that frame because we're in layer 2. MAC address, exactly. The frame has to contain the MAC address because we're talking about layer 2. All right, so now in this example, there is a collision. So in this case, 2 and 5 are trying to send information at the same time, okay? So just wait for the next iteration. You'll see 2 and 5. So 5 wants to send, okay, 1 receives it. Now watch, 2 is going to try and send, and 5 is going to try and send. So they both send, so there's a collision. You see that? So what does that look like? Well, first of all, if it's busy, wait, it isn't. So if it's not busy, we're going to send a frame. Now, 2 devices, so 2 and 5, tried to send at nearly the same time. So the first one that detects the collision, it's going to send out this so-called jamming code. You can think of a jamming code as a busy signal. So it says, hey, look, I sent my message out first, everybody stop, okay? And then basically there are algorithms, back-off algorithms, where once you receive that jamming signal, you have to basically back off for a random period of time. Because let's say, or you use this algorithm to compute how much time, but it would be almost random. It's not going to be the same for each device, because let's say 3 devices tried to put a signal on at the same time, and one of the devices put out a jamming signal and the other 2 stopped. You don't want them to both wait for 1 second before they send out the next signal, because if they both wait for 1 second, then when they send it out, they're going to collide again. So there's some randomization in that built into that algorithm, so that one device would wait a certain amount of time, the other device would wait another amount of time. But the first device sent out the jamming signal, the other devices backed off, they're going to wait. And then that first device, which sent out the successful jam signal, will then continue sending its frame, okay? And you're going to repeat that, and if you have that same issue, after 15 collisions, you're going to just time out. What does that mean? If I time out, what does that mean? Yeah, it's a wait time, but what is it? Basically, I tried to send 15 times, and 15 times I collided. What is that telling me about my network? I sent it 15 times. 15 times it collided with something else. What is it telling me about my network? It's overloaded. It's busy. Exactly. It's overloaded. If I try and send 15 times and each time it's colliding, there's too much traffic on my network. Okay. So that would explain sometimes when you've got bandwidth issues at this level, at the layer 2 level, what's happening. You're just getting too many collisions because too many people or too many devices are trying to put things on the network at the same time. Again, we're baseband. You can only put one signal on at a time. Okay, so that's what happens with collisions. All right, so again, a collision domain is used to describe part of a network where packet collisions can occur, which we saw happens when you're on a shared network or on a network and machines try and send information at the same time. And so in order to get the network to work properly, the machines have to continue resending and retransmitting these packets, which makes it very inefficient, actually. Okay. When you're in a hub environment, and we're going to get into details of all of these devices, but a hub is essentially we're going to talk about how to reduce collisions. That's the whole point of this. So if we for example, have a hub environment, and just quickly, a hub is essentially just a repeater for multiple devices. So it's just like extending your wire. There's going to be a lot of collisions. Even though it's a star topology here, you're going to get lots of collisions. Okay, but then there are going to be other devices here. And then we're going to talk about broadcast domains, right? So broadcast domain is essentially a set of devices like you see here that if you were to send a broadcast, we're going to receive that broadcast traffic from one another, right? So essentially, if you want to limit your collisions, what you want to try and do is what is shown here is create more broadcast domains, right? So if you create more broadcast domains, those domains are independent from one another. If you create independent networks, then you're going to have less chance of a collision. So the idea here is basically, can you split up your network? If you can split up your network, then that's going to reduce the chance of collisions. Okay, and that's when we're going to start talking about the various devices. We'll see which devices we can use to do that and why it makes sense to split up networks. Okay, so you really want to reduce that collision domain, and one of the ways you do that is by splitting up networks and creating more of these broadcast domains. So you asked about the frame. So it's really not that important for you to understand the full detail of what's in this frame, okay? But again, the structure of this frame is defined in the Ethernet framework, or the standard IEEE 802.3. If you had any interest in reading that, you could do it. But essentially, you can see the elements of the frame here, right? But first of all, you have the preamble. So it's a 7-byte preamble, and it's a pattern of ones and zeros again, which indicates the starting of the frame and allows the sender and receiver to establish synchronization. The preamble was introduced to allow for a loss of a few bits due to signal delays, but because today's high-speed Ethernet protocols, you don't really need the preamble. The preamble indicates to the receiver that the frame is coming and allows the receiver to lock onto the data stream before the actual frame begins. So essentially, it's like a warm-up set of bits, okay? Then you've got the start of frame delimiter, which is a 1-byte field, which is always set to a particular value. It's 1010, then 1011, if you need to know that. But basically, just think of it as a specific value that has to be set so that the receiver knows that this is the start of the frame, okay? Then you've got the most important things, the things we're concerned about. You've got the destination address. What kind of address is this again? It's an IP address, right? Correct. It's the MAC address. It's not the IP address. Data link layer, MAC address. So we're putting in the MAC address here, the destination address. Okay. And then you've got the length, sorry, the destination. Then you've got the source address here, which is my own MAC address. And then I'm putting in the length of the field of this frame, sorry. So I tell you how long that frame is. And then you've got the header and the data. Okay, so this is where the data is. Again, the data link layer doesn't know anything about what's in this data. It's called a payload sometimes. We're going to deliver this payload. And at every layer of the network hierarchy, you're going to have an area for data, or you can call it the payload. Okay, it's very similar. Then you have the frame check sequence, sometimes called FCS, sometimes it's called CRC for cyclic redundancy check. But essentially, this is a checksum, a check to make sure that all the bits and bytes were sent accurately. If something gets dropped along the way or is not sent across properly, when you go to compute this on the receiving side, then it won't compute properly, and the other side will know that there is an error. I think I gave you this example before. I teach a lot of different classes. I don't remember who I said what to, but as an example, let me show you an example here. Let's say I just sent, if I was going to send 3 bytes, right? And my first byte was 01, and my second byte was, let me get rid of this, 01, and then my second byte was 02, and then my third byte was 03. What I might do as the CRC, I might say my CRC is just the sum of those, which is going to be 1 and 2, 3 plus 3 is 6. I'm going to add it, and I'm going to get 6. So if on the destination gets 01, 01, and 03, it's going to compute the CRC, and it's going to be 1 and 1 is 2 and 3 is 5, and it's going to say there's something wrong with that frame, and it's going to reject it and ask for it to be resent. Okay, so CRC is basically a check to make sure that the rest of this data has been transmitted properly. Okay, that was a very simple example of the checksum. Usually it's much more complex than that, and it allows for robust frame transmission.